Hi everyone, I'm Ying-No. I'm a PhD student at Yale. I will be the session chair on behalf of my advisor, Professor Ruzeka Piskak, who unfortunately couldn't come. And it's my great honor to introduce our first speaker, Professor Thomas Refs. Professor Refs' research topic cover a wide variety of areas such as program slicing, differencing, and the merging, as well as pointer analysis and data flow analysis. Today, he will give us a talk about program analysis via graph-reachability. We start now.
Okay, thank you. Can I be heard? Okay. Is the audio level okay? I'm not getting a response here.
Yes.
Okay, thank you. So this is a two-part tutorial. Chiron Zhang will give the second half about program analysis via graph reachability. So in the tutorial, we'll cover, I'll cover the first half shown in red here about context-free language reachability, and a little bit about going beyond context-free language reachability, which of course will be the theme of Chiron's part of the tutorial. I'm really not going to say too much about this, but just to give a flavor of some of the directions where what one is computing is not just sort of properties that you can obtain by graph reachability. Okay, so these techniques are applicable to a variety of problems. I will so the first one on my list here is about influence, program slicing, but also is related to information flow and taint checking. And that will actually be used as the bulk of the first part of the talk. But it also relates to data flow analysis questions about whether a certain property phi always holds at P or might hold at P. Points to analysis problems, and just the question of reachability is basically at the heart of model checking. But there's actually an interesting, also a final thing is that there's an interesting paper from a long time ago about whether a crypto-based protocol can reveal a message in plain text can be addressed by the same techniques that I'm going to be talking about here. So these problems are undecidable in general, but the way one addresses it is what one usually does in our community, which is to create a program model from which one can obtain a one-sided answer. And in this case, our program model is going to be a directed graph with labels on the edges of some sort. In this case, just symbols drawn from some alphabet. And then the general question that we're going to get our answers from is node reachable, where reachable is going to have certain different interpretations from what is standard in a data structures class, for example. And then these questions tell you something about the program. So if the program point, I guess I said P, not reachable, but I really meant N. If N is not reachable in the model, means that N is definitely unreachable in the program. And if the node is reachable in the model, it means that it generally means that N might be reachable in the program. So that's the sense in which things are one-sided. So the general problem was defined by Yannakakis in a tutorial paper in the database community in 1990, where he defined what he called L-reachability. So you're given a graph with nodes and edges, and the edges are labeled, but then you're also given a language, and you're given that language in some form, whether it's a finite state machine or a push-down automaton or context-free grammar. But the language L is used to filter paths, so that a path from S to T only counts if the word spelled out by the letters in order as you go along the path is in the language L. So depending on what class of languages you have, there are different complexities for these. So ordinary reachability is a particular case of regular reachability, where you just label every edge with some symbol, say E, and then the regular language is E star. So basically, that just means that any path counts. And as not surprisingly, that can be done very quickly in linear time. But if your languages are more complex, like linear context-free languages or context-free languages, then the complexity goes up. Also, I want to point out that there are new results. There's actually a session with a couple of papers that are related to what Sharon is going to talk in the second part of the tutorial, but there's a result about certification systems for CFL reachability on Wednesday. In terms of my personal involvement in this, I would say that near the start of my career, a few years after I started doing computer science, I was working on attribute grammars, and that led, or I learned things that led to insights to looking at program slicing, which I'll say more about in a second. The answer to that question, or the questions we were mainly interested for program slicing, really were CFL reachability questions, but I didn't know that it was CFL reachability, and only became aware of CFL reachability in 1993. A couple of other milestones. There's a survey paper from 1998 you can find on my webpage that has a lot of different applications and what it was that we knew up until 1998. And there are also tutorial slides from a tutorial I gave at PLDI in 2000. A few years after that, I started to work on what I'll call near neighbors to CFL reachability, and it was only in the last couple of years that I started working with Chiran and his student Wanbo Lee on graph reachability problems again. All right, so let's talk about slicing. So for purposes of this talk, a backward slice with respect to some variable at a program point is the subset of the program that could influence the value of that variable at that point. So here we'll use this program that computes the sum of the integers from 1 to 10, and the backward slice, if we're interested in the slice with respect to this print statement for I at the end of the program, consists of these statements here. In particular, what it's really showing is that the two assignments to sum cannot be influencing the value of I at the program point of interest. So the model of the program that we're going to use is something called a program dependence graph. It's different from the control flow graph. It has essentially the same set of nodes as the control flow graph, but two different kinds of edges. So the control flow graph for the program looks something like this, whereas the control dependence graph is basically the nesting structure of the program with a self loop on the while loop. Technically, these are all what are called true control dependence edges. They're what are executed when they're what are controlled when the predicate is true, and the entry node is considered a sort of pseudo predicate that is always true. But I'm not going to show these labels because they're sort of irrelevant for the purposes of this talk. Then the second kind of edge is flow dependence edges, and these connect assignments to places where the variable it is assigned to could potentially be used. So, for example, this assignment to I could potentially be used at this use of I here. There's also an edge in here, although it doesn't reflect a real dependence. That's just that flow dependence edges are computed by reaching definitions, and reaching definitions, if you are not considering conditions, then this would turn out to be a possible. This would be, the data flow analysis would return that this was a definition that reached this use. So some of these are ones where the assignment, I guess I should say this. The assignment, you can see that there's a self loop on this node. That's because this assignment to I is used on the next iteration of the loop. Okay, so the program dependence graph is just the union of these two edges. And once we have that graph in hand, we can compute slices in a rather trivial way. One point here is that the program dependence graph actually represents a class of programs if it abstracts away from certain orders, linearization in the linear textual representation of the program. So, for example, if we reversed the initializations of sum and I so that the initialization of I came first, it would still be the same program dependence graph. Okay, so now how is slicing done? You start at the point of interest and you just go back and back and back. That's just graph reachability. Okay, one can also talk about a forward slice, which is basically a ripple effect analysis. And so the forward slice with respect to variable v at program point p is the subset that can be influenced by the value of v at p. So that looks something like this. Suppose we pick this point, sum gets 0, and say, suppose we change the value of 0 from 0. Suppose we change the initialization value 0 from 0 to 5 or something. What could be affected? Well, the assignment, or this use of sum could see that effect. And because we're accumulating values into sum, then the final value of sum could be affected. So that can also be computed, again, by reachability, where you go forwards along the edges until you can no longer go, there's nothing further to reach. And that shows that we get the assignment in the body of the loop and the print at the end. Okay, so now to get to context-free language reachability, I'm going to switch to inter-procedural slicing. So all I've done here is taken the two assignments to sum and add that were in the body of the loop, sum and I, sorry, that were in the body of the loop, and I've abstracted the additions by calls to this procedure add, which sits over here and just takes the two arguments and adds the values of the two arguments. So we expect the backward slice to look pretty much the same as it did before, in the sense that it should include this assignment to I, but not this assignment to sum. And because there's this call on add in here, then everything in add is relevant to the value of I at this point. And the key thing to keep your eye on is, how is it that we make sure that we don't include these two elements shown in the boxes in the slice? That's where this notion of L-reachability, or context-free language reachability in this case, comes to our aid. So here we'll use a dependence graph. We called it the system dependence graph, just to distinguish it mainly from the program dependence graph, which was for single procedures only. So there's a program dependence graph for each of the procedures in the program. So here's one for main, and here's one for some program that has been called, which seems to be named P. I guess what I should say is these nodes here in yellow are representing the passing of the parameters from the call site, the actual parameter, to the formal parameter. And then the pink nodes are representing the return value being passed back to the different call sites. So these are, I'm going to refer to these as linkage in edges over here, these two, and linkage out edges as these two edges over here. So for our sum program, it looks like this. where these two yellow nodes are the parameters that are passed in to add at this call site, and these two yellow nodes are the parameters that are passed in to add at the second call site. So for backward slicing, we're going to start the same way. Let's slice with respect to this point here. We'll go back. So that picks up the call node itself, but now we follow this edge back down into the called procedure P, back. And now when we go back, there were two incoming edges to this yellow node. We could go back to this, but the question is, should we go back to that? Well, remember, we're looking for things that influence this point, which was affected by the return value from P. Well, you've never really seen a correctly executing program where the parameter from an entirely different call site essentially directly affected the return value of the second call site. So this red edge seems spurious. And the way that can be formalized is to put a pair of brackets or parentheses on each of the pairs of call and return linkage in and linkage out edges. So we have these green parentheses that mark these, whereas we have red brackets that mark that pair of edges. And the problem with this path here is that what we're trying to do is match an open bracket with a closed paren, whereas in the other path, we had this open bracket with the closed, or open paren with a closed paren. So this kind of matching, which can be more, which can involve deeper nesting if there's recursion, say, is captured by this grammar of matched parentheses, where you can extend a matched path either with an edge or with one of these matching open and closed parenthesis pairs of a certain kind, one for each of the call sites, where in between you can then also have a string that is in the language matched. Okay, so we don't want this, and the way we're going to specify what it is that we want is through this context-free grammar matched. All right, so assuming that we can we can make use of that grammar to filter out that path, what our desire is to go to here and then continue back until we can go back no further using the same kind of criterion. And in the case of the sum program, you can see that that picks up just the first call on add and not the second call, as I was showing. It's whatever magic is going to be behind the use of this context-free language in order to is what helps us filter out, make sure that this call on add does not get into our slice. Okay, so CFL reachability is just the case of L-reachability, where the language is a context-free language. And so this is what we have said before. In the case of inter-procedural slicing via CFL reachability, the graph that we have is the system dependence graph. The language is roughly this language matched. I'll say a little bit more about this later. And our desire is to say that to pick up all the nodes M for which there is an L-matched path from M to N. So it turns out this can be done via dynamic programming. The idea is that what you're going to do is convert your grammar into a form in which every right-hand side only has two symbols. If you have three symbols on the right-hand side, if you have A goes to B, C, D, then you have to introduce a symbol that represents, say, C, D, and then you have A goes to B, X, and then X goes to C, D. So you can do this kind of factoring of the grammar to put it into Chomsky normal form. And then the idea is that if in your graph you find an edge that's labeled B and an edge that's labeled C, then you will just put in an edge that's labeled A. And you'll keep doing this, saturating the graph until you can no longer add additional edges. Now, there's a degenerate case, which you may have learned about in a compiler class, and you may have learned an algorithm that, that allows you to solve this for arbitrary context-free grammars. And that's context-free language recognition, which is sort of the basics of parsing, but it's just the yes-no version of this parsing question. If you're given a grammar, and here I'll just use a simple expression grammar so that it's something you're familiar with, the question is, if I have this string, is that an expression? So the way we're going to do that is we'll create a linear graph. The first node labeled S, the second node labeled, or the last node labeled T, and then the number of nodes that we put in between S and T are equal to 1 minus the number of symbols, so that we have one edge per symbol, and we'll label each of the edges with a symbol from the string in left to right order. And now the question is there an ST path that is in LX? So that's now become this kind of simple context-free language reachability problem. In this case, the answer is yes, and the algorithm should say that. And in this case, where we have an ill-formed expression, the answer is no, and the algorithm should say that it's not. All right, so here's a, let me switch back to the language of matched parentheses. Here's a variant of the language I gave before. It's got two kinds of symbols, parentheses and brackets. And we will be asking the question whether this is a matched parenthesis string. You can see that it is, so the answer is going to be yes. But the question is, how do we get that answer? Okay, so the first step is to take our grammar, and we have to convert it. We have to put it in a form in which every right-hand side only has two symbols. Here we have three symbols. Here we have three symbols. So you can see that we factored, we've introduced these temporary symbols, LPM and LBM, meaning that it's consisting of a left paren and an M, and this is consisting of left bracket and an M. And then we're going to create a dynamic programming table. And this may be, you may have seen this in a data structures class as opposed to a compiler class, because it's one of the canonical examples of dynamic programming. So the table is going to, on the vertical axis, represent the start position in the string, and the horizontal axis is the length of the string. We'll put the symbols of the string along the top of the table. And in the first row, we will put a set that just contains the individual terminal symbols. Okay, so now the question is, how do we fill in the rest of the table? We're going to do this in left to right, top to bottom order. So the question is, and the way we're going to do this is by consulting at each point two cells and seeing whether there is a production that tells you how to extend the table entries. So here, that we had no production that allowed us to put together a left paren and a left bracket to get anything, and so that we get the empty set here. But here, we do have this production M goes to left bracket, right bracket, and so we get to put an M in that table entry. And so we continue here again. We get to put we have a matching bracket pair, and so we get to put an M. Okay, and then at every stage we're going to go down a column and up along a diagonal, comparing cells. So for example, here, we're going to compare this cell to this cell, and then we're going to compare this cell to that cell. This one actually gives us something, a left paren and an M. That was the right-hand side pattern to give us the LPM symbol. And so the result is going to be LPM goes into here. And similarly with other cells along the way here. So our final cell to fill in, we're going to compare each one of these cells in here to each one of the ones, we're going to compare them in order. This to this, this to this, this to this, this to this, and this to this. The only one which doesn't involve empty set is this cell to this cell. There is a match there because we have the production M goes to MM. And you can see what this represents. This M is representing the fact that we can parse this substring as an M, and this M is representing the fact that we can parse this substring as an M. And this production allows us to put those two together, and so we put an M here, and then the question is, this is the root non-terminal of our grammar, and the question is, does this cell contain the root non-terminal? The answer is yes, and therefore the string is accepted. Okay, now we've gotten away from graphs here with these tables, and so what's the connection? Well, let's go back to our problem, and really those table entries were just kind of edge connections. So here's our grammar, and we can do this same process of filling in what are the equivalent of the entries in the graph by means of the process that I showed earlier, the saturation process. So for example, when we put in the table entry that had a singleton M because there was a matching bracket pair here, that was really saying we had a left bracket and a right bracket, and a production M goes to left bracket, right bracket, allowing us to put in this edge M, put in this edge and label that edge M. And so the saturation process is really no different than what we did when we were filling in the table. Okay, and then the final question here is whether are S and T connected by the root non-terminal of the grammar. In this case, they are. There's this edge labeled M from S to T, and therefore the string is accepted. Okay, so this was just for that linear graph that you have for context-free recognition. You can use either a table or this saturating the graph. It's a little hard to figure out what kind of table you want for an arbitrary graph, and so the right model is probably to keep in mind for this dynamic programming problem is that you're just saturating the graph with additional edges, as I showed earlier. Now, for this problem of slicing, that's not quite the end of the story. Let me just use this program to show why it's not the language matched is not quite the right grammar. It's not that we're going to slice this program. It's just I want to show you something about paths in a program that makes calls, and in this case, it makes a recursive call. So this is program P. This is I'm showing the control flow graph for procedure P. This is the control flow graph for procedure main. There's a call on P here. P has a recursive call on P itself, which is why we have these green edges to start the call and to exit from the call. Okay, so one of the acceptable paths in this program is this one here. That's a matched path. This graph also contains this path, but as you can see, that's this first path was a matched path when we put the parentheses and brackets in, whereas the second path was was not a matched path. Okay, but all right. So these matched paths can get, because there's recursion in here, it can get more complex. We're going around, we're making this call, we're exiting from the call, and then coming back out. And here the inner pair of brackets is matched and the outer pair of parentheses is matched. So I showed you this grammar earlier. Basically, what it's doing is it's saying when you have a matched path, it's basically saying you're starting in some stack state, making calls and returns, but not digging into the stack. Throughout the path, whatever is in that stack is off limits. You can go deeper, but return, go deeper again, and return, as long as you don't take anything off the stack that was originally on the stack. But there are some other kinds of paths that we might be interested in. So for example, here, we started in main, we go into P, we get to this call on P, so we go back into P, we come around here, we get another call on P, we go into P, we take the edge that goes straight down and return from P, and now we've gotten to here. Now that's a valid path, right? But it's not a matched path because it leaves us with two unmatched an open parenthesis and an open bracket symbol. So this actually is the kind of, when we're talking about, say, for slicing, when we're talking about influence, something that was in main, say this x gets 3, suppose this has been a printf of x, this could be a path that we want to take into account in which x is influencing the value of x at this point here. But we have a path that's not matched. Well, it's a path which is a prefix of a matched path, and we can capture that by this grammar of unbalanced left parentheses, which makes use of the language matched in this production here. So the way to think about this is that you're sort of using unbalanced recursive calls, recursion in the symbol unbalanced left to sort of generate this path, and then you can put in the matched symbols wherever you need, but you're using unbalanced left to sort of generate the positions, the unbalanced symbols that you have in the string. Now, what in terms of our picture of the stacks, what that is saying is that the original stack is off limits. We're just allowed to end in a situation in which the stack is deeper. Okay, and for slicing, we may also want the other kind of situation where we start in some stack and we go back here, and as long as we don't go deeper than the final at any point in between, but that we don't go dig into the part of the stack that we have at the end, then that would be a path of interest. And so for slicing, these two languages actually play a role, and this also leads into something which is that you may want to also not just use the simple dynamic programming algorithm in solving these context-free language reachability problems, but it can be useful to stage the problem so that you introduce a certain sort of intermediate piece of information that are useful in solving subproblems. So the way this works is that, so here I've just shown multiple copies of the same procedure. In some cases, it's calling something similar to itself. In some cases, it's calling something which is a sort of terminal procedure. In some cases, it's doing one thing, a call on a terminal procedure, and to a different kind of procedure. Okay, so
Sorry, it seems like we lost connections to Thomas for some technical reasons. So maybe let's wait for 5 minutes. If in 5 minutes Professor Refs is not returned, then we may begin our second sessions. Oh, okay. Oh, okay.
So I have a question. At what point did you lose me?
Like 5 minutes before.
Oh dear.
2 minutes before.
And you were seeing slides or not seeing slides?
No, not seeing slides.
So did you see this?
We cannot see the slides. We cannot see what slides you are presenting now.
Wait, you cannot see any slides currently?
No.
Oh,
Okay.
well, that's not so good. Can you see me?
Yes, we can see you.
Okay, and
so in the comments, it says where you cut off. They say you cut off briefly after unbalanced or procedure summaries.
Yeah.
Okay. Okay, but can you see my slides?
Yeah,
Yes,
we can
yes,
see
we
your
can.
slides.
Okay. I think what happened somewhere in the middle, I noticed there was something that actually invited me to the stage, whereas I think that might have been the point at which things got.
Yeah, I think AirMeet disconnected for a second, and then we lost you, and I tried to invite you back at that point.
I see. Okay.
But it seems to be working now.
All right. Okay. Fine. All right. So, but did we? You saw this concept of unbalanced right edges?
Yes.
Okay. All right. Good. So now let me move on to showing how one can decompose the slicing problem using this concept of unbalanced right and unbalanced left. The key to that is what I'll call procedure summaries, and then and then that what I'll show there is that it will actually decompose the slicing problem into a 3-stage process where the 3 stages have different runtime complexities. Okay, so the idea here is, suppose this was a picture of the program dependence graph. Really, it's a sort of subset of the program dependence graph where I didn't want to show lots and lots of edges. So imagine that there are many more edges in each one of these things, sort of black blobs that are supposed to represent individual procedures. So this is our main procedure. There are some leaf procedures here and here and here, and I'm only showing just a subset of the edges for which there are going to be certain connections that we'll see in a second. So the first thing is that down here at the leaves, there are paths that connect this parameter in vertex to this parameter out vertex. So, same thing here, and over here. And because there's this connection, what we'll do is at the call site, we'll put in what we'll call a procedure summary edge that says, if you were to go down in this procedure, you would be able to come back up in via a matched parenthesis path. Now, because these red edges are in there, we can see kind of locally that same thing can be said about this connection and this connection. So we'll put edges
Tom,
in there. Yeah.
Sorry to interrupt, but I'm getting some comments saying that we can't see the laser pointer anymore.
I'm sorry. My fault. I'll go back here. Okay. So here's the path. Here are the two summary edges, and similarly, we have summary edges from here and at these 2 points over here. Okay, now because we have these summary edges here, we can detect this path here, which gives us the ability to put summary edges in at these two places in the graph, okay, as well as some other places. And once we finish, we've sort of connected up all the call sites. Although remember, if we have many other parameters and return values in here, some will have be connected and some will not be connected. Okay, so now what we're going to do is decompose. Once we have the summary edges in hand, we'll decompose the problem by working in the different phases with two different versions of this augmented dependence graph. In all cases, we'll keep the summary edges. In the first or in the second stage, the summary edges were our first stage. In the second stage, we will remove the linkage out edges. So we have no way of coming back from a procedure in this graph. Okay. And now let's suppose this node down here is the node of interest. So as we just follow paths back, ignoring anything about parentheses, we will follow this red highlighted path. Okay. And now let's do the opposite. Let's do the dual. We'll keep the, the problem is there are clearly things down here that can affect our node of interest. But that's not reflected in here because we had no way to get down to them because we took the linkage edges out. In the third stage, we'll take the linkage in edges out, but put back the linkage out edges and continue the slice. Okay, and that allows us to get down to here. So overall, what have we done? The claim is that we have solved an L-reachability problem where our language is not the language of matched parentheses, but the language unbalanced right, unbalanced left. And that the final two phases, we're finding, the second phase was finding the unbalanced left paths, and then the third phase was sort of prefixing the unbalanced right paths to those unbalanced left paths. Now, in terms of complexity, you can see that we did, when in computing summary edges, we were solving the L-matched problem. And that's going to take this n cubed or n cubed over log n complexity to do. But in the two subsequent phases, we weren't concerned with parentheses at all. So those really were regular language reachability problems. And so those can be done in linear time in the number of original edges plus the number of summary edges that you've added. And similarly, so really what we've done is we had this language of unbalanced left, but in place of the matched non-terminal, we were using the pre-computed summary edges that we computed in this phase here, okay? And so this symbol here, this open paren is just a terminal symbol. For purposes of this altered grammar, summary is also a terminal symbol. And so if you look at this context-free language, context-free grammar, it's left recursive. And a left recursive context-free grammar is really a regular language. So that's how we got to regular language reachability, knowing, and that tells us that we can do this with a lower complexity. Okay, similarly for the third phase, we're using unbalanced right, and again, we've replaced matched with summary here. Okay, so let's see. I want to go back to the slide that I showed earlier where I said that our way of dealing with the undecidability of the problems we're interested in solving is to create these models that allow us to give one-sided answers. Now, the program model must over-approximate the program semantics in some way. And then notice, when I said reachable here, at the beginning of the talk, that probably meant you thought of following paths, which is really transitive closure of the edges. Now let's go back to single procedure slicing for a second. And already transitivity can be an over-approximation. So if you look at this program here, where if you were to change the value of y here, there would be no effect on the value of z, or the value of x, at this point, because we're adding, at this statement here, we're adding y's value in, but then we're subtracting y's value out, leaving us with the original value of x at this point. Yet in the dependence graph is not doing anything about arithmetic here, and so you just follow you just follow the edges in this graph and say this path that I've marked, or this set of edges that I've marked in red, is really just the transitive closure of this, and so it would soundly but imprecisely say that that x is potentially affected by a change in the value of y here. Now let's talk about inter-procedural slicing and the role of context-free language reachability and non-transitivity. Well, we've already pointed out that if you, in our sum program, if you change the value of sum, the initialization of sum, you cannot affect the value of I at the print statement in the program. Yet in this graph, if you just consider it a graph without labels marking calls and returns, there is a path. Goes down here, gets to this intermediate node, goes back up here. So why am I talking about that? Because we already had a way of filtering things out. Well, another problem that we posed to ourselves was what we called the chopping problem, which is if you have a source node and a target node, the chop is going to be the envelope of things in between that are used to transmit effects from S to T. Now you might think one way of solving this is that you should slice forward from S, slice backward from T, and take the intersection. That would be this sort of olive green area in the middle. Well, let's see if we do that with inter-procedural slicing. So we do a forward slice from sum gets 0, and everything in green is highlighted, including everything in add. And now if we take a backward slice with respect to the printf of I, we get this red stuff, including everything in add. So if we take the intersection, we get everything in add, although we get nothing in the main procedure. Okay, now, what we argued before, though, is that there's nothing that's transmitting effects from sum gets 0 to the print statement for I. And so the answer should be the empty set. And so the problem was that in taking the intersection of the forward and backward slice, we were somehow allowing this this notion of this sort of transitive treatment of things to creep back in here. So this problem can be solved. There's a paper that I wrote many years ago about how to do this in a precise fashion, but it sort of points up, and this may really be the takeaway from this part of the talk, actually from both parts of the talk, since it's not phrased in terms of context-free language reachability, but L-reachability. In all of these problems, the goal is to model the program with some graph, and then pick a language L such that L-reachability allows you to filter out some of the paths that you don't want. Now, I was going to go through an example about points to analysis, but I think in the interest of time, I am not going to do that, but I now have to figure out what to do here. Actually, you know what? I think I do have time to do this. So let me just blunder on ahead. Let me skip this part, and we'll just go to flow-insensitive points to analysis. So what we're going to do in points to analysis is factor our program so that our statements are of four simple kinds that you'll see in a second. One of them is P getting the address of Q, and we'll have in flow-insensitive points to analysis, you have a kind of global database of where the nodes are the variables in the program. And because we have this statement in the program, we get to put an edge between P and Q. Between P and Q. Second kind of statement that we can have is a simple assignment statement. And in that case, if Q is pointing to some set of nodes, we'll make P point to the same set of nodes. A third kind of statement is P gets the dereference of Q. So in this case, we have a more complicated pattern for what Q may be pointing to, but we have to go 2 levels down from Q, but we make P point to those. And the fourth kind of statement is an assignment indirect to P. Okay, so in that case, whatever Q is pointing to, the things that P are pointing to are made to point to those S's. Okay, so in the case, here's a simple program where actually just one pass through the program is enough to sort of fill the graph. We get to put an edge from A to E here. Now B gets to point to E, or has to point to E. C is pointing to F after the end of this. We follow star B, and we make it point to whatever C points to. So E is pointing to F, and then D gets to point to whatever star A is pointing to, and so D gets an edge to F. All right, now there are various ways of formulating this, and I'm going to show you one that's based on CFL-reachability. But to get there, I'm going to take you through something that is not CFL-reachability, that is interesting in its own right, and is one of these near neighbors to CFL-reachability, namely data log. So earlier I showed you this slide about how to solve CFL-reachability via dynamic programming. There's another way of looking at it, which is that we're really using the following data log rule, where I'm using sort of small letters A to represent my capital non-terminals. In data log, the literals, the symbols in literals are small letters, and the variable symbols are capital letters. So that's sort of at variance with context-free grammars, where capital letters are non-terminals. So I hope it's also color-coded. So but I hope you can understand what I'm trying to say here. So so the issue is that you can, if you give a right to left reading of the data log rule, saying if we can find an appropriate B fact from some X to Y, like this edge here, and a C fact that connects Y to Z, then we get to put in, then we have evidence of an A fact from X to Z. Okay, so notice that there's a pattern here. This is what's called a chain rule, where every literal on the right-hand side, the variables are linked. The last symbol goes to the last variable goes to the first variable. Okay, and similarly we have here. So it's the first over here goes to the first variable here. The last variable here is coming from the last variable here. Okay, so we can set up points to analysis by, for each of the four statement kinds, we're going to put in a fact that says your program has an assignment statement that does something with these two variables. And then our points to rule is simply a data log rule that that says if you have, in this case, it says, if you have this assignment statement of this form, then you get to put in a points to fact that connects P to Q. Okay, similarly, this rule here is saying if you have an assignment from P to Q and points to facts that connect Q to some R's, then you have a points to fact from P to the R's. And likewise for these more complicated statements. Now, if you look at these rules, what you'll see is that they are, oops, let me go back. So a rule like this one is a chain rule. We start with P, that's the first symbol here, P to Q, Q to R, R to S, and S is the last symbol here. The problem is this rule here. This is not a chain rule. We start with R is over here. Well, you could say, look, we could sort of flip things around, but we still don't have the right order of things here. We'd like to flip these two around, then we would have the right thing. We end with S, S, Q, Q, P, P. If we flip these, so that sort of suggests that we ought to have anti-points to facts. So if we had something like this, then we would have a chain program, which suggests what we ought to do is just flip these points to facts around. But the problem is those points to facts are not, this is the first symbol, this is not the first symbol. So this rule is not a chain rule. So we can't do that. But there was a former student of mine, Dave Melsky, had a clever way of addressing this, which is basically to say, we're going to put in the flipped assignment statements, and now everything works out. The way we're going to create our chain program is by this schema. We have to do some rearrangements, but we're basically sort of doing everything in the reverse direction and flipping things around. But then in our problematic rule, so all of these rules with either all black or all red with the bars over the symbols. But here we have this mixed one. And so it turns out that when you sort of dualize that one, you end up with things, and both of these are chain rules. S is the first symbol here, S to Q, Q to P, P to R, R is the last symbol over here. Okay? So by these means, you just say, here's my context-free grammar, and now it's a CFL reachability problem. Okay, so I said that that there are some near neighbors to CFL reachability, and one of these is data log itself being used for program analysis. I mean, there I went through some contortions in order to take a particular problem specified as a data log in terms of data log and convert it into something that was CFL reachability. But I don't think that's not always possible. I want to just say a few words about one thing that for one of these other mechanisms to show sort of something that either cannot be expressed as CFL reachability or would be hard to express as CFL reachability. So here, the issue is how to model your program so that you're correctly modeling local variables. The thing about local variables is that they need to be reestablished in the state that they were in at the call when you get back to at the end of the call. And one mechanism for doing this is something that we call merge functions, where you can sort of think of the model as being that global variables go this way, they go down into the called procedures, but local variables follow a sort of a different path that doesn't go down into the procedure at all. So this is like the correct for something like Java, where the local variables in the stack are completely off limits when you go into a called procedure. Okay, whereas at a different call site, the path would be something like what is portrayed here. All right, I'm going to skip this slide. It was a bit of a joke anyway. Okay, and let me just finish with some old references to this material on context-free language reachability, the original paper by Yannakakis that had nothing to do with program analysis, but the use of this concept in databases, and then my survey paper and slides from an earlier tutorial. So with that, I've gone a little bit over. Let me stop and take questions.
Thanks. So let's begin questions in Israel. Okay.
Hello, I was just wondering, in particular for the matched parentheses case, I can't really work it out on my head, but isn't there potentially a more efficient way to do it than, full CFL reachability? Like, I feel like you could whip something up with a Dijkstra and a stack, or like,
Sorry, I missed the last comment. You could do something with what?
I feel like you could probably whip something up with, Dijkstra and a stack and some sorcery or something like that, but I can't do it in my head. But it feels like one of those things where like you don't need the full generality of the algorithm being applied, since it's just matching, matching parentheses basically.
So one of the problems is that if you look at the set of paths, the path that can contain, a path that connects S to G by some match parenthesis path can actually be exponentially long in the size of the program. And so if you're just trying to do some sort of exploration where you make use of a stack in order to keep track of things, you may have to do an exponential number of pushes and pops to complete that exploration, even if you knew where you were going and made the correct choices at every one of the stages. So you can think of, there may be a version of that where what you're doing is tabulation or memoizing as you go along, but that in effect is what what the dynamic programming algorithm is doing, is that it's tabulating paths that it's creating a table entry or an edge that is evidence of a path that you've already encountered. So I think what you have in your head is the right model, except that the CFL-reachability algorithm is actually doing what you want your intuition, it's really a manifestation of your intuitive algorithm.
And thanks. Is there any question?
I'm curious if the first technique, the matched parenthesis technique, applies to some unorthodox control flows such as exception handling or context switching.
So so again, with all of these problems, you sometimes have to make over approximations in order to create the model that is going to give you sound answers. But the question about exceptions, there you have to there the answer is that you would switch to a different context-free language that would be not just match parentheses and not just the unbalanced left and unbalanced right that I showed, but a language of what do I want to call it? A language with a kind of exception parentheses. Actually, let me back up and make an analogy. So in some Lisp systems, there's a terminating parenthesis, close parenthesis symbol that basically says close all open parens. Okay, and it's just a convenience so that you don't have to type paren, close paren, close paren, close paren, close paren. Instead, it's like close bracket, and it means close all the parens. So that's the sort of thing that you need for exception handling. That you're going to have an sort of an open. Let's say that this is a bracket symbol. So you're going to have an open bracket at the try block, and then no matter how deep you are, how many open parens you have, the closed bracket is the thing that says go back and match to the try block. Okay, and now you can say, well, wait a minute, is that really going to be a context-free language? Well, there, you know that what you can express with a pushdown automaton is a context-free language, and it's clear that there's a way of expressing what I just described with a pushdown automaton. It's going to be a pushdown automaton that whenever it sees one of these open bracket symbols, it's going to push a symbol on the stack. Whenever it sees an open paren symbol, it's going to push that on the stack. When it sees a closed paren symbol, it's going to match the closed paren to the open paren. But when it sees a closed bracket, it's just going to pop the stack until the next matching closed bracket. So you do something like that to model exceptions.
I think there is another question in this room.
Thank you. Hi, Professor Reps. Thanks so much for the great talk. Brendan Considine from University, and I'm aware there's an algorithm by Leslie Valiant that kind of does a similar thing for context-free language parsing, and I believe he shows where you can convert this into Boolean matrix multiplication with this special. Be useful for program analysis, or do you have to define this in a specific way for the kind of analysis and for these kind of these specific problems where you have to construct a certain kind of path algebra? What other schemes are you aware of that allow you to do this efficiently? Thanks.
So unfortunately, the audio blipped out about halfway through for maybe 10 seconds. So I'm not sure I heard the entire question. You had gotten through you had mentioned the Valiant paper from I think 1974. So that paper was about context-free recognition, and it was showing that you could do context-free recognition in time as fast as you could do Boolean matrix multiplication. So that is for chain graphs, although I believe he was basically doing a matrix closure, and actually he was closing a matrix, and I think his same construction works for upper triangular matrices, arbitrary upper triangular matrices, and but for chain graphs it was just a sort of upper triangular matrix that had a distinguished form. What that result is that you could adapt that result to program analysis for programs that were not recursive. You could do a sequence of Boolean matrix multiplications, sort of working your way up the call hierarchy, but that doesn't apply for analysis of recursive programs, because you would no longer have the upper triangular form.
I see. So you can't always reduce this, reduce recursive programs iterated matrix multiplication because it's self-referential.
Correct. Well, and I believe you lose the upper triangular form. I think that's also what happens.
Okay, makes sense. Thanks.
There is another question from remote audience. So thank you for interesting presentations. Slightly non-technical fashion program slicing is a well-studied field, yet I rarely see it being built into today's standard development tools, right? One could imagine future to answer in your demo. Are there still research problems that need to be solved in order to make slicing practical as a tool for developer? Do you have any insight on this? Thank you.
Well, so I think one problem is concurrency, is that many programs written today are concurrent programs, and there are technical problems to be solved in, people have looked at it and there are algorithms so that's one question. That's one answer. A second answer is that in many cases, you end up, the result of a slice is that a large chunk of your program influences your point of interest. And so that ends up not being a very interesting answer. It does provide some focus, but I think what's happened for slicing in particular is that people found that it wasn't, it sort of didn't illuminate enough to be all that interesting. I use that mainly just to show that, because it's an easily grasped problem, and to help get across the ideas of what L-reachability can help you with. I think it's unfortunate that we don't have slicers. I think that they could be useful in many situations, but the world just didn't go in that direction.
Thank you. Let's give applause to thank you, Professor. I think that's the first part of